This brings us to our last exercise. We're going to violate one more assumption, which is that the attacker can't possibly observe or otherwise intercept this conversation that occurs between the badge and the reader after they've authenticated each other. And this assumption might potentially be invalidated if, I'll try to zoom in a little bit. Hopefully you can kind of see that. If, for instance, an attacker were to install a skimmer on the reader, which just records every transaction between any badge and the reader itself. If the attacker were to do that, come back a few days later, grab the skimmer and see the message log, well, they'd still see the data being exchanged back and forth between the badge and the reader. They'd see all the UIDs presented. And that could potentially give them a lot of actionable information on how to attack the system. Or maybe they're able to install a device in such a way that it can capture transmissions from the badge before they get to the reader, or vice versa, in which case they can actually modify messages like read sector 0 and turn that into read sector 2. And if the badge replies with data, maybe it modifies that and gives to the reader new data. And so, the attacker in this case can do much more to actively manipulate the system, even though both devices have authenticated to each other. The attacker just still has this ability to kind of mess with our security system. And so we don't need authentication at this case. We just need confidentiality for the messages that are being sent back and forth between the badge and the reader so that the attacker can access them. So in exercise 5, we are going to apply that encryption to the conversation after the two devices, the badge and the reader, have authenticated each other. You can kind of see down here, we're going to use AES, which is a form of symmetric encryption, to hide those messages from even an attacker that can observe or intercept them. Okay, so in this scenario, the top part all the way up to this small box here on the left proceeds exactly as it did for exercise 4. The badge presents its UID to the reader. The reader sends the nonce. The nonce computes the HMAC and sends it back. The reader can verify that and know that it's talking to an authenticated badge. The badge sends its nonce. The reader sends the digital signature back to the badge. The badge verifies that signature, and now it knows it's talking to an authenticated reader. At this point, the devices need to compute a key to use in that AES encryption, and it has to be a key that the attacker doesn't have knowledge of. So we're going to apply kind of the same process that we did in exercise 3, where we gave each badge its own unique device key that the reader could derive. We're going to do the same thing here. We're going to give each badge its own information key, which this diagram is a little old, so a couple of places I refer to this as the session key, but session key and info key are the same thing, basically. The badge will get that at build time, and that's also a key that the reader can compute on the fly. So here's down here, again, I call it the session key, and I incorrectly say that each is computing this, but this is a value which is already in the badge. The reader performs the same process that it did to derive the device key, which is do the HMAC of the fleet key and the UID to get that session key. The only difference is we want these to be separate keys. Right? We want key separation because we're using them for different purposes. So we're going to add a little identification string to each of these HMAC algorithms that makes sure that we get separate values. So in the first case, we're going to compute device key using the fleet key, the badge's identification value, and just this string badge underscore auth. And so that'll get us one device key. Down here, when the reader computes this key, it'll do the HMAC of the fleet key, the UID, and a different string, info underscore encryption. It's used to derive the session key or info key. At this point, both the badge and the reader have this info key or session key, and they can use that to do AES encryption of the messages being sent back and forth between the badge and the reader. And even if an attacker is listening or kind of in the middle of these transmissions, it doesn't get access to the information being sent back and forth, and that protects the information, at least for this conversation alone. There are other concerns if the attacker, eventually is able to extract the information key from the badge and has record logs of past conversations, but that would be an exercise 6, and we got to stop the workshop somewhere. So the, the information key, the encryption key that the badge has, the reader derives on the fly, then gives us that confidentiality when those messages are being sent back and forth. So the last exercise then is exercise 5. We jump right into the yellow because this was a stretch goal even for the workshop. But the yellow exercises are here are just like the red ones in the previous exercises. You're going to run the code, see it working, compare it to exercise 4 to see what sort of security principles we gain now that we're doing this sort of encryption on the messages being sent back and forth. And there are a couple of green exercises to kind of extend your understanding. So if this seems cool, take a crack at a few of those, and then we'll move on to the final video.